Hello, I would like to talk a little bit more about rock structures, in particular a little bit of review and some new information perhaps, and an answer to a question that was proposed in class about how do we know that higher confining pressure enhances or leads to more plastic deformation. So it's hard. This understanding folded rocks is not easy because it involves looking at them from different perspectives. So let's see if we can maybe shuffle through this a little bit. So here is a model, if you will, a diagram of a big fold. Here are some trees for scale. So it's essentially a big hill. This is an anticline because we have layers that are folded in this orientation. And here's a feature called the hinge line, which is at the crest, the top of the fold. And these two guys are called limbs. So notice that the layers dip in this direction over here, and on this limb they dip in that direction. The oldest rocks, when we're looking perpendicular to this hinge line on this face, are here, and the younger rocks are located here. So this is a non-plunging fold, horizontal hinge axis. So if we went up in an airplane and we looked at an eroded portion of a folded area, we would see something like this. Here's the axis of the anticline and the axis of the syncline. Notice the layers dip away from the anticline and towards the syncline. And this is where I was talking about how in the interior, the cores of eroded anticlines, you have old rocks that get progressively younger as you move away. In the syncline, the younger rocks are in the core, and the older rocks are on the outside. So it might also be helpful if we took a little walk along this traverse to see what the rocks might look like. So the rocks I'm about to show you aren't exactly related to this map, but hopefully they'll illustrate this process. So on this limb of the anticline, I would see layers. This is perpendicular to the axis. I would see layers that dipped in this direction. If I moved to the axis area, I would see layers that were changing direction. Some are dipping that way, some are dipping this way. And here is the hinge line right there. And if I moved over to here, the rocks I would see would be dipping this way on the limb of the syncline and dipping inward on the other limb. And these rocks up here are the very youngest. So if we put this all together, here is the anticline and syncline. It's actually a syncline, anticline, syncline pair. And here is the crest, the hinge line or the axis, they're all the same, of the anticline. And here's the hinge line right here of the syncline. So I hope that helps a little bit, because now we're going to get a little bit more interesting. So here we have is a plunging fold. Okay, what that means is that the hinge line is not horizontal, but is actually inclined to the horizontal by this distance. We still have limbs on each side of the anticline, and we have the oldest rocks on the inside, the youngest rocks out here. So here's a diagram that I got from the internet. Here is a block that shows the face that is perpendicular to the hinge line, and then the map view, which you'd see if you were flying over in an airplane. So here's the plunging anticline, plunging syncline, plunging anticline. Okay, so here are the important things. If you see a map view, like you're up in an airplane, and you see closure of the folds like this, that indicates that these folds have a plunging hinge line. That is, it's not parallel to the ground surface. In the anticline, notice that the rocks in the interior of the anticline right here are older than the rocks on the limbs. Okay, so that is a marker of a plunging anticline. A syncline is the opposite. The youngest rocks are in the interior, the core portion, and the older rocks are on the outside. I mean, this is a really cool pattern, and those are the two things that we need to know. If you see closure, it's a plunging fold. If the rocks in the interior are older, it's a plunging anticline. If they're younger, it's a plunging syncline. So let's take a look at some other examples of this that kind of mimic this map. So here's a map view as if looking down from an airplane. You can see the closure here of the fold, and here you can see the closure. Notice that these dip inward, therefore it's a syncline. These dip outward, it's an anticline. Old rocks, young rocks. So here's the sheet mountain anticline. It's a plunging anticline because we can see the layers fold around. Okay, if we were to look on this limb, the layers would dip in that direction. And if we were to look in this area, the limbs would be dipping in that direction. Okay, oldest rocks, younger rocks.
We can also look at a plunging syncline, which is at a much different scale than the previous map. This is an outcrop scale. Once again, you can see that the closure, the fold has this closure that you can follow along. And notice that these limbs dip inwards towards the axis area. And in this case, the older rocks would be down here, and the younger rocks are up here. So this is a plunging syncline.
Faults. Okay, so I didn't cover some of the terminology with respect to strike-slip faults, okay, and I want to do that. So there are two types of strike-slip faults. First of all, here's our block. The fault's at an angle, so therefore we can identify the hanging and the footwall. And here is a igneous feature called a dike that goes across the block. Okay, so notice that this dike has been moved to the right. If we were standing here and looking across, the layer would have the apparent displacement of moving to the right. And this is called a right lateral fault, or strike-slip fault.
The opposite type of fault is the left lateral fault. And once again, here is our block diagram with an inclined plane, so we can identify the hanging wall and the footwall. And this igneous dike is our marker that we can use to determine the direction of movement. So if I was standing on this block and looking across at the footwall, you'd notice that the offset would be to the left, so that makes it a left lateral. Now if I ran across here and turned around and looked back at the hanging wall, it would be the same thing. So this marker moved left relative to that. That's why they call this a left lateral fault. Strike-slip fault.
Okay, there was a really good question in class about how do we know that confining pressure leads to more plastic flow. Well, the one answer is that when we go look at rocks in the field, we see rocks that are at higher pressure tend to have more plastic or ductile features to them, like folds, for instance. Whereas ones that have lower confining pressure, that formed near the surface or were deformed near the surface, they tend to have brittle structures. They've also done experiments on rock cylinders. So here's an experimental device. Here's a rock cylinder drilled right from a rock. It has a jacket around it of copper. The tectonic stresses are modeled by using these pistons, and we can monitor the pressure. And the confining pressure, or how deep the rock might be, is modeled or regulated using a fluid, a hydraulic fluid that's pumped in around the cylinder. And we can measure that too. So we can measure the amount of stress, we can measure the confining pressure, we can also measure the strain, the amount that the shape has changed by just measuring the rock cylinder. Okay, and observations are important as well. So here are some actual rock cylinders that have been deformed or stressorized at different confining pressures. So here's low stress, doesn't look like it's changed much. Here's higher stress under low confining pressure, and the cylinder has faulted and broken brittly. At higher confining pressure, that behavior is suppressed and you get some shortening still, that is, it's gotten smaller, but there's been flow instead of fracture. So this result indicates that at higher confining pressures, the material deforms by flow rather than fracture. We can also look at 3 different rock types, A, B, and C, and see how the type of rock determines its behavior. So A, okay, on this graph we have stress increasing that way and strain increasing that way, strain being a measure of how much the rock cylinder changes. So A cylinders, cylinders of rock A behave brittly as you increase the stress, and notice that the strain does not increase that much. On the other hand, B does not respond brittly but actually ductily, as you can see by this barreling, and then starts to flow. Okay, so you get large amounts of strain without much increase in the stress, and C as well, but even less stress. Okay, so it needs less force to make the rock flow. So take this data and make some graphs. Once again, stress, increasing change. Okay, 3 rock types. The linear parts of these graphs are the elastic strain. So presumably, if you release the stress during this part of the experiment, those rocks would go back to their original shape. Sometimes it's permanent strain, but not a lot. So this rock behaves brittly. It breaks along faults, and therefore the amount of stress drops. Okay, and this is important for earthquakes, which we'll talk about later. Now B instead shows this linear trend, and then the amount of stress levels off and the rocks begin to flow. Okay, so in this one, the rock flows at high stress. At rock C, the rock begins to flow at a lower stress. And these lines here are measures of the maximum strength, yield strength of the rock, where it should behave brittly under certain conditions. So I think.
So that concludes this short structure extra. I hope some of this information helps clarify stuff we talked about in class, as well as answered some questions. Personally, as a geologist, deformed rocks always fascinated me, and it's an area that I continue to study. And one of the things I want to make sure that we connect to is that understanding these structures help us to figure out tectonic settings for rocks, even when the tectonic boundaries have changed over time. And our next challenge is to look at tectonics and structures and understand earthquakes, because that's kind of the focus of our project. And so our next subject area will be looking at earthquakes and the resulting impacts of them on society. Thanks.